Dear audience, I have the honor today to present a part of my research work entitled High-Rate Sodium Nickel Zirconium Phosphate as an Electrode Material for Sodium-Ion Batteries. That work was carried out in MSN department at Mohammed Polytechnic University. The rapid development of renewable energies and electric vehicles has led to a very high demand for energy storage systems. In this regard, different technologies of energy storage have been developed, but the electrochemical devices, and specifically secondary batteries, are the most suitable technologies for these applications due to their flexibility to electricity systems, their high efficiency, modularity, and their fast response time that they provide. The performance of these systems is highly dependent on the electrodes material. The phosphate polyanionic materials have attracted increasing attention due to their excellent electrochemical performance and versatile structure. Among these phosphate polyanions, we can find the Na3N sodium superion conductors, which are indicated as one of the most favored frameworks to provide phase stability on cycling in sodium-ion insertion systems. Add to that, they provide a low price and they are safer compared to other materials like the layered oxides, for example. Our phosphate-based material was synthesized through a simple Sorgel method. Firstly, the following raw materials were mixed and stirred in an aqueous solution, then heated up at 60 degrees Celsius until complete evaporation and gel formation. After that, we proceed to a calcination for 9 hours at 750 degrees Celsius with intermediate grinding. As we know, phosphate-based materials have a poor electronic conductivity, so for that we proceed to a carbon coating in order to increase it. Our material was mixed with an appropriate amount, 15% of the total weight of the material, with in an acetone solution, then calcinated for 5 hours at 600 degrees Celsius and the continuous flow of argon. For the structural characterization, the XRD analysis shows a well-crystallized sample with hexagonal symmetry and electricity space group with the following cell parameters. The comparison with those of good enough groups confirmed the accuracy of our refinement and the stability of the material. Raman spectroscopy analysis was conducted to check the carbon coating process. We can notice the appearance of two bands, which refer to the G and D band characteristic bands of carbon. Thermogravimetric analysis was also employed to determine the amount of carbon. We can notice that we have 3.55% of the total weight of the composite material. The morphological analysis shows uniform and well-shaped particles with an average particle size of 1.5 micrometer. Also, we can notice the presence of some agglomerations in the coated sample. Concerning the electrochemical test, cyclic voltammetry is performed at the scanning rate of 0.2 mV per second. We can notice a cathodic portion at 0.8 until 1.2 volt, while an anodic portion appeared at 2.2 and 2.4 volt. We didn't notice any significant difference from the first cycle until the sixth, which indicate the stability of this phosphate material. Concerning the galvanostatic test, our material was tested in a half sodium electrochemical cell between the potential window 0.01 until 2.5 volt at current density of 25 milliampere per gram. It delivers an initial charge capacity of 121 milliampere hour per gram and a discharge capacity of 140 milliampere hour per gram. Also, it presents a good efficiency of 98% after 25 cycles at 25 milliampere hour per gram. This phosphate-based material was also tested at different current densities. We can notice that the capacity still remains 19 milliampere hour per gram at the current density of 500 milliampere per gram, and it's stable compared to the other current densities, which indicate that our material works very good in high rates. So to conclude, the pure phase of sodium nickel zirconium phosphate was successfully synthesized by a low-cost Sorgel method. Electrochemical tests show good discharge capacity and an excellent stability at a high current density. As a perspective, we are seeking to perform forward analysis, such as in situ X-ray operando, to well understand intercalation and disintercalation mechanisms of our phosphate-based material. And thank you very much for your attention.